So let's say we have a series, and that series is kind of complicated, and it can be hard to figure out whether or not it's going to converge. So one thing you can do is you can say, all right, look, I'm just going to take the absolute value of that sequence that I'm taking the partial sums of. And what we know is that if I take the absolute value of that, it's always going to be greater than or equal to the actual terms of the series. So if that's true, then we can use the comparison test that says, look, if the absolute value of these terms converges, then the regular series has to converge, because that's kind of the definition of how the direct comparison test works. There's a little bit of tricks you have to do. You have to separate kind of like the positive and the negative ones and things like that. But that's not too bad. It's not too hard. But the idea is, I say, look, I'm just going to take the absolute value. If it works, it works. That's an important piece, because what it allows us to do is say, look, this series, this is complicated. I'm just going to take the absolute value of it. So if we know that if that converges, we can say this converges. Nice. Now, if this does converge, which is the nicest case, we say that this thing is absolutely convergent, or it converges absolutely. And what you'll see is that terminology is persistent along different mathematical constructs. There's a term like integrable. We'll say that something is absolutely integrable if you can take the absolute value of the function and integrate it. So keep in mind that absolutely something is a term that comes up in math more than just here. So we say it is absolutely convergent. Now, if we find that when we take the absolute value that it doesn't converge, then that's disappointing, because it's kind of work that we've done for nothing. Because it's possible that the original sequence or the original series does converge, even though the absolute value doesn't. And that can happen in cases, and we'll see this over here, and examples with like alternating series is a really good example. So if this converges but it doesn't absolutely converge, we say it's conditionally convergent. So the reason we say it's conditionally convergent is that there's some condition on the sequence that causes it to converge. So I'll actually start here for that particular case. I've got -1 to the n times 1 over n, right? The 1 over n is a well-known, it's a harmonic series. We know that it diverges. But with that -1 to the n, that becomes an alternating series. And since this is both positive, or since this piece is both positive, it's a decreasing sequence, and the limit of the sequence is 0 as n goes to infinity, we know that this particular series is going to converge because it's an alternating series. Okay, so I could say that, okay, well, a sub n is just this term here. The absolute value, though, gets rid of that alternating term, because -1, that -1, whether it's 1 or -1, the absolute value always turns it into just a 1. So if I take this series, well, that series diverges, right? It's a harmonic series. It diverges. We can take the integral test. It's also a divergent p-series. But we know that this does converge because it's an alternating series that we've already covered. So we say that this series is conditionally convergent. So we just need to be careful that we don't confuse those, because if you know that it's absolutely convergent, sometimes when you're doing other mathematical operations, you can say, oh, well, it's absolutely convergent, just throw an absolute value on it and just kind of move along your way. But you can't always do that. Now, in this particular case, this is a really good example of why you would want to use this sort of theory. Cosine n pi over n squared. Cosine n pi is kind of ugly. Now, if you plug in n equals 1, it's cosine of pi. N equals 2, it's cosine of 2 pi, 3 pi, 4 pi. And if you know your unit circle, cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, and so on and so forth. So you end up with this alternating behavior. But that's not even the most important piece. So for example, you might have something where it wasn't cosine of n pi. Maybe it was cosine of square root of 2 pi, or something weird like that. Why would that be important? Well, what ends up happening here is, now in this case, when we take the absolute value, it just becomes a 1, because that's really just an alternating term. This is just a fancy way of getting an alternating term. But this wouldn't be. that wouldn't be a fancy way of an alternating term. In fact, that would definitely, it would go different ways. But what you do know is this, is that cosine is bounded by -1 and 1. So if you take the absolute value, you get that, which means that by the direct comparison test, sorry, that should have been an n pi there, sorry, square root of 2 n pi. You know that that's true, so you know that that's true. So when you do the absolute convergence, you can then use that absolute term, and you can directly compare it to something that you know is a convergent p-series. And that's really the power of doing this, is you can take your absolute value and then you have something that's positive. And so then you can say, okay, well, what's something that's simpler that I know is going to converge, or what's simpler that I know is going to diverge, and I know it's greater than or equal to that, or whatever. So the whole point of this is stringing all of these different techniques together to try to resolve something that converges or diverges. Now, in this particular case, again, it converges. It's a p-series. So we know that this is an absolutely convergent case. And we're going to do some examples here, and hopefully that'll really kind of clear up and solidify how we use this.